Welcome and thank you for coming to my Viva voce. My name is Patrick Golec and I've worked on this project with Dr. Vlad Stolijan. The project focuses on CNT wires for audio signals. I'll begin with the motivation and hypothesis behind the project, continuing then into the background and the theory, which lead me to conducting the experiments that I did, which provide me with the results to make a conclusion and some statements about the possible future work that could expand the project further. The hypothesis is that carbon nanotube wires have the potential to outperform copper wires in the processing of audio signals. However, more importantly, why should we consider carbon nanotube wires as a replacement for copper wires? Well, CNT wires are a porous network conductor, which give them different properties from solid conductors, such as copper. These properties make them beneficial for transmitting signals. Other benefits come as a result of material properties of carbon nanotubes, such as high thermal stability, corrosion resistance, and flexure tolerance. What initially interested me in this project was the potential application to future research in CNT wires for signal transmission. One of the properties to consider when investigating CNT wires is quantum conductance. Individual CNTs behave as 2D quantum wires, wherein they conduct along channels with high density of states. This is done through ballistic conductance, which is when electrons travel through a medium unimpeded. In theory, this would result in a medium having no resistance, as the only thing limiting the conductance of a material would be the density of states of the channels and the number of channels. In practice, however, this is not perfect, as electrons can be deflected at the contacts or through interaction with phonons. This results with there being a resistance. The energy of the channels depends on the chirality of the carbon nanotubes. This is further shown by a Kataura plot, which plots the diameter of each carbon nanotube against the separation energy. The first line that you see on the graph would be corresponding to the first Van Hoven's principle. At this point, the first channel of a semiconducting carbon nanotube begins to conduct. This can be further expanded upon by finding at which diameter the semiconducting CNT begins to conduct at room temperature. Room temperature corresponds to 38 millielectron volts. Using the Kataura plot, we can find that the diameter of a CNT that conducts at that temperature will be 13.77 nanometers in diameter. A benefit of using carbon nanotubes as opposed to copper is the reduced skin effect. When an AC signal is transmitted through a wire, most of the conduction occurs at the surface of a wire, which is because there's no electric field in the middle of a conductor. The electric field is generated at the surface of a conductor, and the field itself is evanescent, which means that the closer it gets to the core of a conductor, the weaker it is. This is further accelerated by a higher frequency. There are already methods put in place to make copper affected less by the skin effect into a stranded wire composed of many small diameter wires. Taking this into consideration, carbon nanotubes are one of the best materials to use when considering skin effect. They have a very small diameter and they are hollow. This means the skin thickness would need to be incredibly small for them to even be affected by the skin effect. A challenge with using CNT wires comes mainly from the contacts. Firstly, CNT wires are very fragile and they break easily. As such, care needs to be taken when contacting them. For example, they cannot be contacted with solid conductors and should instead be contacted with fluid adhesives. However, since CNTs are hydrophobic, they're difficult to coat with fluid adhesives. Care also needs to be taken when actually conducting measurements of carbon nanotubes, as any touch with a measurement instrument, is going to break the wire. This is what happened to my first sample, which is seen here. Another problem with metal contacts is the formation of a Schottky barrier. This forms between a metal and a semiconductor, and the height of the Schottky barrier is determined by the difference of the work function of a metal and the electron affinity of a CNT. Both of those are variable. The work function of a metal obviously will change and depend on the metal used for a contact, and the electron affinity depends on the chirality of the carbon nanotube used. Luckily, there's been a lot of research done in Schottky barrier metal CNT junctions. Palladium was an especially good metal contact to use for CNT wires. The Schottky barrier isn't the only source of resistance in other contacts, however. There are other unknown resistive factors that play part in resistance at the contacts. It's been documented that the resistance at the contact is actually higher than the theoretical height of the Schottky barrier, implying that there are some other factors at play here. I had to prepare a new set of samples. I've made 8 in total, using mainly glass and filter paper as my substrates. I've used the same silver contacts as used in the previous sample, and I have found through image analysis with ImageJ that my wires were somewhere in the region of 400 micrometers in diameter. Also, their lengths ranged between 6.1 and 33.2 millimeters. Overall, this gave me a pretty good sample with relatively constant diameters and a variety of lengths to work with. In order not to repeat the same mistakes as with a previous sample, I've decided to add measuring wires in order to not directly contact the carbon nanotubes. This was done using a relatively thick steel wire because I wanted the contacts to be relatively rigid and difficult to move if I didn't ideally want it to move. I've also used solid tape to secure the measurement wires. This was done in the case that if the measurement wire broke away from the contact, it wouldn't move and damage the carbon nanotube right next to it. Overall, this strategy turned out to be extremely successful. None of the wires broke, which is a better result than I was expecting from the security method. The first experiment I've conducted with this set of wires was measuring the resistance at a DC current. This was done using a multimeter, and here are the results obtained. The graph on the right shows how the resistance of a wire varies with the length of the CNT. This is used for working out the average resistance per length of the wire. It can also be used to find the contact resistance, as at length 0, you would only get the average resistance at the contacts of the wire. That was obtained to be around 2.2 ohms. The humidity and wetting experiments were conducted during the first semester, and thus I still had access to the labs when I conducted them, which also means I've used my first sample set to conduct these experiments. The purpose of these experiments was to test the significance of the hydrophobicity of carbon nanotubes. Since CNTs are hydrophobic, if you get a clump of them, as a wire, for example, and surround them with water, they will aim to reduce the surface area as much as possible. This is to maximize the surface energy. This results in the diameter of the carbon nanotube decreasing. I wanted to measure whether simply increasing the humidity in the air would cause this effect to occur, or if this effect occurred at all by dropping a water droplet on the CNT wire directly. The video on the right shows the droplet experiment, which has resulted in an increase in current flowing through the wire, and conversely a decrease in its resistance. This is significant as a decrease in the diameter of a wire caused an increase in conductivity, the opposite to what would be expected with copper. On the other hand, humidity was not enough to cause this effect, and thus an increase in humidity doesn't actually change the conductive properties of carbon nanotubes. This is a very positive result, as you wouldn't want a transmission wire to change its conductive properties based on the humidity in the air. Protecting it from water is much easier, as you would just need to enclose it in a waterproof coating. The main experiment for this project was always to measure the characteristic impedance of carbon nanotubes as a function of frequency. This is accomplished firstly by designing a circuit that's capable of measuring the impedance of a component. I first designed a circuit that measures the impedance of a component for which I know the frequency response. The component used was an aluminium electrolytic capacitor of value 420 microfarads. The smoother lines are for the aluminium electrolytic capacitor, meaning that I would expect it to have a smoother curve to it. Also, I would expect the impedance to decrease until it reaches a resonance frequency at which it would begin to increase again. Since my capacitor value is 420 microfarads, I would expect its frequency response to be somewhere between 10 kilohertz and 100 kilohertz. And this is exactly what I find. When I've conducted the experiment, the impedance response was as follows, which looks very similar to the theoretical. Also, I found that the turning point was indeed between 10 kilohertz and 100 kilohertz, suggesting that my initial hypothesis was correct. This demonstrates that my circuit is indeed capable of measuring the frequency response of a component, and I can use this circuit further to test other components. Before immediately measuring the impedances of actual carbon nanotubes, I wanted to conduct a mock experiment where I measure an impedance of a different material, in this case, a carbon fiber. The reason for this is I was scared to damage the carbon nanotubes, which was an issue with my previous samples. I therefore chose to get more accustomed to the circuit by conducting this experiment. What was particularly challenging with this experiment was that now I had 4 probes to work with, and if any of those probes would have touched a carbon nanotube, it would have broken. This was therefore a pretty good experiment to do beforehand. It also showed me how the frequency behaves with different lengths of wire, which allowed me to make some predictions for how the carbon nanotube experiment would go. What was found and what was expected was that the impedance of the wire increased with the length of it, which is shown on a graph. But what was more surprising and useful for the future experiments was that the stability of impedance actually increased with the length as well. So the length of wire now becomes a benefit as the impedance response became more stable. This would be especially useful if carbon nanotube results gave me the same pattern where increasing the length made the impedance response more stable. It would imply that simply increasing the length of the wire would automatically make a better transmission line. This experiment was the biggest out of the ones I've conducted during my project. It involved measuring the impedance of the carbon nanotubes, and I've done so through the use of a circuit seen before. However, I did need to change some things in order to make the circuit more compatible with how my carbon nanotubes are connected. Primarily, some of my probes needed to be connected together, and because of the COVID restrictions and me having to conduct the experiment in my room, I had to use steel wire to wrap around 2 separate probes in order to actually contact them. I was then able to connect the steel wire coming from the probes to the steel wire connecting the carbon nanotubes. This allowed me to have 2 channels being sent to my laptop in order for me to measure the RMS voltage and the frequency of the signals. The next step was to find a good frequency range to actually analyze my carbon nanotubes. So the function generator I've worked with was up to 5 megahertz, which was high enough of a hypothesis as it covered the 20 kilohertz audio frequencies. However, I was unable to find the full frequency response of carbon nanotubes with such a limited range. What I was able to find was the point at which the impedance began to decrease. I therefore decided to tailor most of my measurements to be mostly around when the graph begins to tilt and where a peak can be observed, which can be seen in the first graph. In total, I have taken over 400 measurements, 23 per wire for 18 wires, which allowed me to get a very consistent pattern that can be seen. I've also found the phase shift with an increase of frequency, which gave me an interesting result. The dip occurred at a different frequency than the dip observed with the magnitude. This is very interesting, as I would be expecting the the dip to occur at a resonance frequency. This would imply that the CNT samples had either multiple resonant frequencies or there was some other factors at play which affected it. Overall, I was very happy with the results obtained. The impedance increased with the increase of wire, which was exactly what I was expecting, and the stability of the impedance was very good for all values. The pattern I've predicted from beforehand, essentially all lengths of carbon nanotubes, gave me a very stable frequency response, which allowed me to show the pattern so well. On the other hand, because my frequency range was so limited, I am unfortunately unable to show the full frequency range of the carbon nanotubes. Also, since the phase shift and the magnitude of the impedance seems to have different fundamental frequencies, I'm unable to predict what kind of pattern would emerge at higher frequencies. The results from earlier also allowed me to reverse the graphing and plot the impedance against the length of the wires at different frequencies. This allowed me to obtain the contact impedance, which would be the intersect of this graph. The effect of frequency on the contact impedance was inconclusive, as although there was a trend that increasing the frequency decreased the contact impedance, the uncertainty in the measurements was greater than the difference, so that alone is not conclusive. However, if we compare the results for impedance with the results we got for the resistance of the contacts, we can actually find that it's different by around 2 ohms, which is greater than the uncertainty. This seems to imply that the contact impedance does have a reactive part to it. This might play a part when considering high frequency signals, although for my audio frequency range, this won't affect anything. Although for my audio frequency, the impedance can be said to be constant. Also, for the audio frequency range, the contact impedance can be said to be effectively constant. Since it was previously shown that decreasing the diameter of a carbon nanotube does not make them less conductive, it's better to use the mass of the carbon nanotubes as a comparison to copper. The masses of the carbon nanotubes have been recorded, and the diameter used for the calculation was 400 micrometers. If the mass as well as the length of the wire is taken as a constant, we can use the density of the copper to work out its diameter, which would happen to be around 34 micrometers, around 10 times smaller than the carbon nanotube wires. This would also give us a gauge of 47. Using the obtained diameter, the length of the wire, and the resistivity of a copper wire, we can find that the resistance of the wire would be around 0.19 ohms. The specific conductance of the CNT wires used for this experiment averaged at around 50 Siemens per meter per gram centimeters cubed. We can then use the resistance, length, mass, and diameter of the copper to find its specific conductance to be around 6,500 Siemens per meter per gram centimeters cubed. This shows that our theoretical copper wire is around 100 times more conductive than our CNT samples. This result was expected, as my samples were a mixture of carbon nanotubes, which were also undoped. Although I found that the copper was more conductive, the carbon nanotubes still have a huge potential in outperforming it if the conditions are met. In terms of the future work for this project, I can see it going in 2 different directions. You can either improve the samples and make them more conductive so that eventually you can prove that a sample of carbon nanotubes can be more conductive than copper, or you can continue analyzing the carbon nanotubes at different frequency ranges. This is to analyze whether they can be used for transmitting signals other than audio range. Lastly, to comment on the project management. During the first semester, I managed to keep to the plan very well, as the labs were open and I was able to make constant week-by-week progress in terms of the experimentation. However, due to the COVID restrictions implemented in semester 2, I was unable to conduct many of the experiments that I was originally planning to do. This caused me to have a much more theory-based focus, which was actually beneficial to the project. So overall, I'd say managing this project has been successful. Thank you so much for listening to my presentation, and I will now be taking questions. Feel free to ask anything if you're curious about any parts of a project. Thank you.